Okay, hey guys. You getting ready for that?
No, we're waiting.
So, you already gone?
We're about to go.
So remember, don't stand in front of this. I mean, just stand, yeah. Okay.
company Third in this presentation, our company's Third will talk to you about what they have learned over the course of this week. They will talk to you about the different kinds of energy and how they are transformed to other types of energy.
Okay, so does anybody know what energy is? Oh, my bad. Okay, my name is Cadet Brown. I'm from North Carolina High School. And yeah, okay. So, like I said, does anybody know what energy is?
Yeah. Work is energy.
Did you read that off the book?
Yeah.
That's the answer. Okay. So, energy is the ability to do work and make things happen. It's also associated with the state or condition of one or more objects. Energy is conserved. It cannot be created or destroyed. The characteristics of energy is that energy can be transferred from one to another object as well as transformed from one type to another. That's not your side. Change it.
I'm Cadet Janet from Robinson.
Louder.
I'm Cadet Janet from Robinson High School. These are the components of energy: kinetic, which is movement, potential, location, and place; internal, which is the inside energy. This is the types of forms: mechanical energy, thermal energy, chemical energy, nuclear energy, radiant energy, electric energy. And this is some of the life events, how energy.
Okay, so right here, as you can see, this picture, it says types of energy. So right here, mechanical would be a leaping frog or a moving car. Thermal would be melting ice cream or heating a soup.
Electrical, which is power lines or lightning. Chemical, lighting a match or food for people to eat. Nuclear, from sun and blood. Yeah.
I'm Cadet Hegler and I come from West Carolina High School. I'm going into the 11th grade. And we did our information of transformations of energy. Transformations are a part of everyone's life, and everyday tasks such as pretty much picking up this pencil here and dropping it is a transfer of energy. Everyday tasks have been transformed, has some form of energy transfer no matter what. Energy transfers can be big or small depending on what action is being performed. Transformations of energy is a change from one type of energy to another. An example would be dropping a pen would be potential energy to kinetic energy.
Good afternoon, Alpha Company. I'm Cadet Roberts from Cleveland High School, and this is about Rube Goldberg. Does anybody know who he is before we start? Who is he? So nobody knows who Rube Goldberg is.
Yeah, I watched the video.
Well, Rube Goldberg was an inventor, and he originally started out as a comic book / political artist for the New York Times. And he basically did complex machines to do a simple task. Like, I don't know if any of y'all have ever seen it, but it's a complex machine, and at the end, the clock wipes his mouth after he eats. And Purdue was actually the first college to ever do the Rube Goldberg machine competitions, and those started in the 50s. And in his machines, you needed all the parts to really be all one after one and no mess ups for them to actually work. And you can only do them one time.
This here is actually a clip of a video of some of the devices that have been made by the Purdue schools.
3, 2, 1, fire! The whole team is confident in the trophy, exactly. It's always going to be the thing that you weren't working on. Of course, that's the thing that breaks.
We don't know it now. It just keeps moving.
What is it about Rube Goldberg machines that turns mild-mannered engineers into mad scientists? Perhaps we should start at the beginning.
Hey y'all, I'm Cadet Joyner from Lawrenceville High School.
And I'm Cadet Lopez from Thomasville High School, North Carolina.
Alright, so our topic is circuits. So, what is a circuit, you ask? A circuit is a complete circular path where energy flows through. They have three main components. You have your conductor, your energy source, and your complete circuit.
So what are the kinds/parts of the circuit? There is a closed circuit, an open circuit, a short circuit, and the parts, like she said, are the energy source, which are the batteries, the bulb, and the wires, which are your conductor. So here we have an open circuit, which shows that the bulb is off, which means that there is no energy flowing. And then over here we have a multimeter, which measures the voltage of whatever is running. So right there, it's like a motor. And then we have the two batteries that are connected, and that is a closed circuit, which flows the energy through.
Circuits and how they work. There are two different types of circuits, parallel and a series. So right here is this is the parallel circuit, and both of them go on they have the same power source, and you can take this light out, and this light bulb will still go. And then this is the series circuit, and if you take one bulb out, all of it will completely stop.
All right, good morning, I'm company. My name is Cadet Mendez Garcia. I'm from Blackfoot High School.
And I am Cadet Mansura. I am from Trenton High School from North Carolina. Our presentation is about turbines and generators. A turbine is a wheel powered by fluids.
And that could be through the movement of air or liquid.
Wind turbine is powered by wind.
Which is, of course, from the movement of air, like windmills.
Water wheel powered by water.
Which can be occurred by the rotation of blades through flowing water, like streams and rivers.
Kinetic energy moving blades.
Okay. My bad. So this is the process of how a turbine works, the physics of it. So the kinetics moving through the blades, such as the flowing of fluids like gases and air, liquids, like I mentioned earlier, rotates the blade, which is kinetic energy, or the kinetic energy comes from the flowing of liquids. And by moving the blades, that creates electrical energy.
Electrical energy is also created from mechanical energy.
And how mechanical energy becomes electrical energy is by rotating the parts within a generator, which creates electrical energy, which can be used by the consumer. This video is showing a stream of water going through blades, and I know it's a little hard to see, but there's a little part right here by the blade, connected to the blade, which is a rotor, and the rotor is turning the parts within this generator and this cylinder, and that's creating electrical energy, and that electrical energy is being used. And the electrical energy is used to power this LED light, which is right there. Alright.
The earliest turbine built was 1,000 years ago, thousands of years ago.
And this was located in the Middle East, and it was used to ground the grain. And this turbine was usually a water turbine because they utilized the flow of water to power their machines that ground the grain.
And then later on, Romans used the same technologies.
So they also utilized water turbines. However, they had aqueducts, which meant that they didn't really have to use naturally bodies of water flowing water, so they can pretty much use that machinery anywhere.
And then Charles Bush managed to develop a large-scale wind turbine
in the 19th century, where he connected the wind turbine to an electrical grid.
And then soon, four plates turbine soon downgraded to a 3-plate turbine.
Because having 4 blades was inefficient, because the windmill would have turned slower, so 3 blades were more efficient, and now common in today with wind turbines.
But 2 blades are also still used certain places.
which would be the ocean, because in the ocean there are some places where the the air pattern is more favorable, where having 2 blades is easier than 3 blades. Because having more blades, you got to use more energy, but with 2 blades in the ocean, it's just more favorable.
And inside the generator, a conductor surrounded by a magnetic field.
Which is when I mentioned earlier, the parts within the generator. That is the conductor surrounded by a magnetic field, and that's how electrical energy is created. Alright, in this video, I am blowing on a wind turbine, which again is moving a rotor with moving the parts in the generator, creating light in the LED light.
I'm Cadet Cruz.
I'm Cadet Nick Taft with Pickens.
Solar energy. Energy created with photons and electromagnetic waves travel through space. What does any of that mean? Because that means absolutely nothing to anybody, probably. No, okay. A photon is a particle of light. So a photon would be traveling along waves like this. The electromagnetic spectrum, this is all possible this is all possible solar energy right here. And right here is what we can see. We call that the visible light spectrum. Well, when these magnetic waves are traveling through, obviously solar energy comes from the sun. So what we get here on Earth is mainly these UV rays, because the other rays are blocked by the ozone layer and other layers of the atmosphere. How it's gathered in properties of solar energy. Solar panels taking light and using the photoelectric effect, converting it into electrical energy. The photoelectric effect is when light hits a material, knocks an electron loose, creating a current. A current is just a flow of electricity. That's all that means, is that it is flowing to wherever there is a positive charge. The PN junction is the space between the positive and negative sides of the panel. And by using this fact of the photoelectric effect, you are able to create a current that flows throughout wherever you want it to go. So in this image right here, in this tangle of wires, there's light hitting these solar panels. So when the light hits these solar panels, it knocks the electrons loose within the solar panel in a process you can't see. And that creates a positive and negative charge. And the negative charge goes through these wires and through this bulb, which then creates the light that you then see.
And solar panels are made up of like probably about a dozen smaller cells, which are able to capture the light. And the cells have the electrons inside them, and the cells can actually also function off of lights like these, but a lot more, probably a lot closer. And that's actually how we got that to light up. We got it to light up inside of a room like this. So you don't need direct sunlight, but it's the most optimal. There's some pros and cons of it. Number one being the pros. Let's get the good part out of the way first. It's almost unlimited. As it comes from the sun, it'll expire in about 6 billion years or so, so I think we're good for now. It's a clean source of energy that does not produce waste. It's a widely available resource, and the technology improves rapidly. Over time, it's improving constantly. Unfortunately, it's less effective in days with clouds and wintertime, and it is completely ineffective at night. It's new and expensive, very expensive, and they have to charge batteries for night use of energy. However, they are producing more and more solar panels available to the public at a cheaper price that have more energy output on them. The current ones have 15 to 20% energy output efficiency. However, the maximum right now is 46 that was made in a lab with a 46% collection. and they're just making more and more and more.
Good afternoon, Alpha Company. Good afternoon. So this slide is about thermal energy. Thermal energy is the vibration of atomic particles in objects. There's three types of ways that thermal energy can be transferred to other objects. One is by conduction, which is the transfer of energy through direct touch. And then convection, which is the transfer of energy through a liquid or gas. Radiation, which is the absorption of and emissions of light. And heating is when you add thermal energy to an object. Cooling is when you remove thermal energy from an object.
The IR panel is maps out the IR radiation, which is the infrared radiation. This is the cold pack.
You're quiet. No.
This is a cold pack, and this is our cadet Sam.
Speak up. You can do it.
This is Cadet Sam.
Speak louder, please. You have to speak loud. Y'all speak loud.
Make it first shot.
What about your mask?
His voice is low, that's okay. Would one of the other cadets like to explain what has a voice still?
All right, so this is an IR camera. IR camera is maps out infrared radiation. This is a picture of Cadet Hegler. As you see in this photo, this is a cold pack. He's holding it in his hand, and you can't see the infrared radiation through the cold pack. Go back to the last slide. You'll see infrared cameras like this that are non-contact that will detect temperatures in places like restaurants, especially during a pandemic where you can't really use thermometers that you put in your mouth that you would have in a doctor that beeps. Yeah.
Temperature correlation of thermal energy of an object.
Okay, so there's different ways we measure thermal energy. Fahrenheit, this is the one we use in America. 32 degrees is the freezing point. 212 degrees is the boiling point. In Celsius, it's a much easier way of measuring thermal energy. 0 degrees is the freezing point. 100 degrees is the boiling point. In science, we use Kelvin.
That just means no thermal energy. It's burning fossil fuels that get trapped in the Earth's atmosphere and heats up the Earth.
I'm Cadet Lawrence, and I'm from West Berlin High School.
I'm Cadet Edgar from Eastern E equals mc squared, was created by Albert Einstein. E equals energy, m equals the mass, and c equals the speed of light. Nuclear, the process of fission converts mass to energy. The atom, or nucleus, is split in the fusion process to get the energy. The nucleus consists of protons and neutrons. The protons repel each other, and because they are both positive. The protons are able to stay in the nucleus because there is a mass defect in the nucleus. It is a mass defect that is converted into binding energy.
The binding energy keeps the protons and neutrons together in the nucleus. Nuclear engineers are interested in the bonding energy when they split the nucleus in the process called fission. The bonding energy is the nuclear energy that can be converted to an electrical energy, electricity. Nuclear energy is the only source of energy that is available at all times. Nuclear decay. Some elements are naturally unstable, hence they are said to be radioactive. Radioactive elements are always changing, decay to new elements. Every radioactive material has a decay rate.
every element that decays gives out or emits radiation. Radiation can be alpha, beta, or gamma.
And this picture is just us representing an atom. It's neutrons and protons that are equally, are equal, and they give equal resistance.
Good afternoon, Alpha Company.
Good afternoon.
I'm Cadet Penix. I'm from North Carolina, JROTC High School. And in this presentation, Third Platoon basically told you guys what energy is and give examples on how it really makes up our whole world, and different examples like Rube Goldberg machine and how a simple everyday task can be turned into a complex system, and how we use these things every day in like rivers and stuff, like the difference between turbines and generators, and like I said, how it brings our everyday world together by just using natural resources.
These are all the cadets and the professors that helped us, along with some undergrads that also helped us teach us how to do circuits and learn about these different energies and things like that.
So let's go ahead and give a round of applause to professors and
I would also like to add that we're always looking for new energy sources because we can't always rely on different fossil fuels. So having stuff like nuclear engineers that always come up with new ways to finding new energy sources is very important.
I'm going to assume we have some time for questions since you guys started before I was here to start the timer, but we do have some time for questions.
In your research, exploring all the forms of energy, if we were to switch to one, primarily right now, which source do you think would be the most effective and the most efficient?
Nuclear. Me personally, I would think nuclear.
Yeah. You want to know why? Why is nuclear?
I would like to know.
It's the most efficient, and it's also one of the ones that don't, it doesn't really pollute the earth as much as other things like coal and natural gases.
However, it's very hard to put a nuclear reactor in a car. So that may be one difference.
So how exactly did heating and cooling relate to thermal energy?
It relates to thermal energy because heating is when you add thermal energy to something. So like all y'all know about radiation because y'all stand outside all the time in the 90-degree weather. You're hot all the time because of the sun's radiation on you. So that's how it relates to thermal energy because you have an increase of thermal energy whenever you stand out in the sun or anything like that. All the different types of ways you can transfer energy that relate to it. Okay.
So I've looked into hydroelectricity using the water. Well, I didn't use the water, correct?
Yes, that's right.
Okay. Is that efficient enough? Like, is that a possibility for the future? Like something to look into? Or does it kind of, it has to be downside?
So I got to answer that. So I'll use an example for when we were experimenting with the water play. So you remember the video with the flowing of water?
Right.
So it has to be like a high speed flow of water or else it won't produce as much energy because the blades have to spin at a high speed in order to rotate that rotor, as I said, turn the parts of the generator to create electricity. And when we were using the sink, using the slower speed of water didn't really light the LED bulb, but using higher speeds, of course, light it.
And the reason why that matters is because not every place on Earth, so that's why it can't be as widely available, is because not every place has high-speed rivers or streams to be able to use hydroelectricity.
Oh, yes, and also with water, we use, it was very hot, of course, it's been hot these couple of days, but we use paper towels, spray them in water, and kind of use them on ourselves, and that further helped us understand thermal energy and also helped
first one.
It's called the bathroom.
Yes.
Okay, so I don't know if y'all answered this while you're presenting, but when you were talking about the solar panels and the light, is that on for the visual, like what you can see, the colors and stuff? Is that like what side of that on? Is that on like towards the microwaves or towards like the solar?
Visual light spectrum is directly in the middle.
So the UV lights are directly on the middle?
No, UV light should be on the left side, then there's visible light.
Yeah, so like what's the light that the solar panels use? What light, what side is that on?
That's the UVs because it has the highest frequency. So it doesn't have the highest, it has the higher frequency.
Yeah, the solar panels will actually absorb visible and infrared and ultraviolet.
It absorbs all.
They'll work with any of them.
So you said nuclear energy was the best compared to the rest, correct?
Correct.
What about like nuclear meltdowns, nuclear winds? Because aren't those like pretty big drawbacks to nuclear energy itself?
So the thing about nuclear meltdowns is that how many nuclear meltdowns can you really name? Probably 2.
They were pretty severe though.
They are pretty severe. However, through maintaining of nuclear energy is in fact the only energy source where you can directly contain the waste, and this waste is stored in like underground bunkers far away from people so that it can emit radiation and decay over time. And because of that, it is actually a very safe form of energy as long as it is maintained.
It has to be highly maintained. The more famous meltdowns that you've probably heard of, those nuclear power plants were not maintained even to a good standard.
Yeah, let's give the physics team a hand. Somehow, and again, I was out of the room dealing with something with the commandant there, so we are ahead of schedule, so we're going to go ahead and let the mechanical team get themselves organized. Once they're organized and ready, we'll have the next presentation. So you guys can have about 5 minutes to get yourself organized and do what you need
Thank you.
does your on the diagram thing, hey, who's everybody on the diagram thing? I just said the legs and other Okay, so you're going first. Are you doing that rising senior?
No, just series. Just series.
High school.
High school.
I know, that's the thing. That's
Okay, let's have the cadets get settled again.
Actually, I'm gonna put my mask on every time y'all say that.
Okay, we're going to go turn it over to our fourth presentation, which is the mechanical engineering group. 30 minutes starts now.
Good afternoon, everyone! Good afternoon! I'm Cadet Metzloff from Grimsley High School.
I'm Cadet Spicer from West Rowan. I'm Cadet Perez from Audrey Reynolds. I'm Cadet Rodriguez from Heidi Trask High School.
I'm Cadet Davis from North Rowan High School.
I'm Cadet McCormick from East Surrey High School.
I'm Cadet Hicks from Grimsley High School.
I'm Cadet Revis from Mount Tabor High School.
And I'm Cadet Gracewell from Indiana. And today, we will be introducing you to...
Manufacturing is, no.
We will be introducing you to subtractive manufacturing, specifically traditional.
Manufacturing is the practice of taking raw products and resources and forming them into desired products.
Specifically, traditional or subtractive manufacturing is when you take that raw material, you take pieces away from it, and then turn it into a desired product or whatever you wish to make. With traditional manufacturing, you do it manually, which means you use your hands and tools, not machines, no computers, just hands and tools and specific things that help you cut away and take pieces away from it.
The lathe machine was invented in 1718 by Russian engineer Andrei Nartov. So we, the lathe machine, we take this piece, as she said, and we're going to put it in that little jar right here. This little jar.
It's called the chuck. Chuck. Chuck.
So we open it and we do this. So, we, like she said, we start taking pieces away. It goes this, and this. Then we get a finished product. This is the final. We use this stuff for our technology. If it wasn't for this machine, we wouldn't have many of the technology we have today in our society.
These are parts of the lathe machine. Specifically, as we said, that's the chuck that would hold the raw material. Now these are the specific things that can cut into it. This is a hand wheel. It can move it left or right, so you can position where you want to cut into your raw material. The tool post specifically holds the blade, or whatever tool you're using that will cut it in shape. Different blades can make different cuts.
The legs, obviously, put it up. The bed catches the shavings that you take off, and the feed rod is what helps it go left and right.
Hello, guys. So, this is what you call a veneer caliper. So, I'm going to demonstrate some things with this tool. If I can get it out. Okay, so as you can see on the board, so right here at the top, this is what you call the inside jaws. So let's say if you have a hole and you want to measure the inside of the hole, you would take this part of the inside jaw and just stick it in it and measure it to whatever number you want to measure it. The bottom part right here is called the outside zone, which basically you will measure horizontally. All you have to do is measure to wherever you want to have it and just stick it right there. Also, I'm going to tell you some of the names that you would on the measure. So the top and the bottom is called the main scale. The top is what you measure in inches and fractions. The bottom part is what you measure in millimeters. So, for an example, if you want to measure, let's say 0.1 millimeters, you would set it to that exact measurement. So, let's say, like they said, the chuck. You would place this raw material inside of the chuck. If you wanted to make a simple mark of where you want to shave off the metal, all you have to do is put the raw material in the chuck and carefully place wherever you want to have your measurements. And all you have to do is take the hand wheel and just put it close to the raw material, and as it's moving in a circle, well, towards you in a circle, it will cause a little line all around.
This here is the turning tool. There are many different types of turning tools, such as the right-handed roughing, the right-handed finishing, and the right hand facing. They all do different things, and what their main thing they do is shake down the raw material to what it looks like, such as this. And we have the right-hand turning tool, which would make the groove right here, well, not the groove, but slope. Make it go at an angle, like right here. How it slopes down right here, that's what this tool would do.
So our group's focus was traditional manufacturing. Traditional manufacturing is just hands-on process, which you're using specialized tools to make a desired product. It's not used as much anymore because of the advancement in technology, but when used, it's usually for commissioned pieces that you cannot find on the market.
Any questions?
So, I understand you said it's subtracted. I'm wondering which one is the actual final product, because the one on the far right.
Both are technically final products. We just have them side by side.
Okay, so the both. Okay. And is it supposed to be anything specific? Or could you give it a name?
What we made specifically wasn't any part to something greater. We were just given little measurements that we can do and just to have fun and see what we can cut out of the raw material.
Did you have to make any serious mistakes, like anything like chop half the material?
Yes. So with the machine, the lathe machine, if you were to stop using the machine, like let's say if you were cutting too much off, or well, okay. So when you're using the lathe machine, metal pieces are like constantly moving all over the place. So I was constantly getting hit with metal pieces. Okay, it's not fun. So I was constantly getting hit with metal pieces. So my partner here, she decided to stop. That is a bad thing to do. Do not stop the machine, because if you do that, what it was going to cause is, I'm going to pass this around, but you would see that there are like little tiny like levels of metal that is cut. So I will pass it around. You can pass it back. So when you look at it, you'll see that you would have to go all the way back, start all the way over, and yeah, start over.
So about how long will it take you to reach your finished product?
Depending on what you're making, it could take hours, days, even weeks or months, because you're doing it by your hands. So you are specifically cutting into it, making all the cuts, and depending on how long you can last, just cutting and cutting all those hours, that depends on how long it will take. Why would you make something manually? You would make. Shoot, sorry. You would make something manually if you.
Here you go.
You would make something manually if you want to have a commissioned piece, a piece you cannot find on the open market. Like if you're making a very specific machine that you want to design, you want to create, you would have to use manual manufacturing to do that, like doing it yourself, because you can't find that on the open market.
So this is so you had to manually with your hand move it in the lathe.
Because I don't think a knife could cut another
Right,
metal.
I understand that, but it's always like that. To me, it got lost in translation. Yeah, so the lathe did the cutting. Correct?
Yes.
You just had to fix it.
You use tools and other machines to make it.
Yeah, we had to move the blade to get the precise cut. That's how we got all these angles and how we shaped it from this to this. Just by moving the blade back and forth, up and down to get it precise.
Also on the machine, when we put it in this spindle, Chuck, it spins. If you didn't know, it spins, so all the cuts are usually even across the whole thing.
And I can add to that, there's a switch on the right side of the machine that turns it on and off. So if you turn it up, it's going to spin the opposite way. But if you turn it down, it's going to spin your way. And that's what you want, because if you don't, your product will be messed up.
Any more questions? Last one.
Why will they be messed up if it turns the other way?
Because of how
It'll mess up the blade. Because if the grooves are used to and how the blade's set, it'll end up just tearing it off, wearing it down, make it wearable and even fight. That was the last question.
Special thanks to our
Oh yeah,
professors.
special thanks, Mr. Warren and Professor
Thank you.
Yeah. Thank you.
Why you broke it?
So I'm right here.
I'm back here. Tara, you're back here first. You're back here. We can get out of this.
White.
We're getting an order to create
Y'all are in the camera. Move back.
McDonald's, go over there.
Are you ready? Hey, could you do it
Good afternoon, Alpha Company. Our project is on computer numerical control manufacturing, also known as CNC. I am Cadet Morales. I'm from Glenn High School, and I'm a rising junior.
I'm Cadet Weaver. I'm from Cleveland High School, and I'm a rising senior.
I'm Cadet Hudboy, but known as Mustache, and I'm from Cleveland High School, and I'm a rising senior.
I'm Cadet Alcantara. I'm a rising sophomore. I'm from Baptist Hills.
I'm Cadet White. I am from Overhills. I'm a rising sophomore.
I'm Cadet Alejandre. I am also from Overhills, and I'm a rising junior.
I'm Cadet Joseph Soto. I'm a rising senior, and I'm from Andrew Jackson High School.
I'm Cadet Indiana. I'm a rising junior at Bluffton High School.
Okay, so this is just CNC basics. It's basically telling us the functions as we use a tool, and this is the alphanumeric codes and special characters. So we would put these in our machine, and it basically gives the directions of how to use it. This program is written and then inserted into the control unit, which are controls. Which is why it is subtractive. Sorry, it takes away raw material using coding tools, and this is why it's subtractive manufacturing. And another reason why it can be mass produced.
No, it's yes.
Right here is an example of a part and the dimensions for that part. Typically, unlike traditional traditional fabrication of it using the lathe, we use CNC, which is a computerized version of that. So all you really got to do is press buttons or put code in. The it still can be just as complicated, just not as much physical, but more in your head, doing calculations of numbers and remembering all the different codes, like T codes, which are for tools, G codes, which I think are for specific directions. And so compared to a traditional manufacturing, instead of having to move spindles and stuff, you're mostly pressing buttons. And as we go on, you'll learn that you can also use a grid, but that's on the slide. Also, so this is an example of the operations and the way they go. For facing, you're just pretty much cleaning the material so it's not sharpened. It doesn't have edges, so it looks nice and clean when you're finished with it. You also have turning, which is just it's spinning around. You also have chamfer, which is making a bit of a edge on it at an angle, but inside of material. And you also have tool part position, which which is the tool going back in its original position, because there's something called a tool changer, or they call it, what do they call it again? The turret. And so on the turret, it has different tools. So instead of having to manually change a tool, typically you can just load the tools that you need, and depending on the machine and the size of the machine, you can have more tools. Like the one that we used here had 4 tools that you can go through, from what I saw. So you can do 4 different types of cutting instead of having to literally take out the tool or the cutting blade out of the lathe and swap it for another. So it saves a lot of time. It also tends to be faster and do cleaner like cuts and stuff. It also is a lot more precise than using your hands and your eyes, since it is computerized. And so this is just an example of, from the earlier slide, you also saw this, of the codes for programming. So you usually have to type these in, and that's what you call like manual CNC. That's what some people call it. And it's when you manually type the code, but most of the time there's like a grid system that you can use. So that's on there.
Alright, so there's the grid method, which is we found to be a lot easier than manually typing and writing code. So basically it cuts the cylinder into like a 2D shape, and you'll plot it on this half, and it'll symmetrically reappear on this half. So you just like design all the cuts. You can put it into, if you want like exact coordinates, you can type that into. We just clicked on the graph for fun, and we printed it out. It was cut it out. I'm sorry. It was extremely easy. Way easier than typing in the code. It took not even a minute.
You don't have to memorize code.
You don't have to memorize anything. That's it.
So a few benefits for CNC over traditional. It produces objects a lot more efficiently, a lot quicker, and with less scrap, because unfortunately we are not perfect, so we have to have, sometimes we make mistakes and a part can be ruined, so you have to make a completely new part, and it takes 4 times that as well. Next slide.
Okay, so in our class, we use the Boxford 180 machine. It's a disc-type turret with 8 tools on it. You can change out the tools if you need to, depending on what kind of shape you want to make. And it can handle mild steel, wax, brass, or aluminum. This is brass. It took about 2 to 5 minutes, way less than the manual process. This came out 2 to 5 minutes. And what I just said, depending on the material, it's gonna come out less or more time.
That's an example of the machine right there. These are the controls. Unlike a typical, like what I was saying earlier, lathe, instead of just the best manual control of it are buttons. Instead of having to move like 6 different spindles and latching stuff on and changing tools, it's all right here. And that's the inside of it. That's the jaws where you'll load the piece in. So when it starts to spin, there's a tool changer right there. It spins and rotates to change the tool depending on where the tool is. And that's the motor that allows it to move up and down. And it's a 2-axis machine.
Okay, so now we're going to pass it on to all of our teammates and what their experiences while working on our pieces. So whoever wants to go.
I go first. So I took a class for this stuff, so I know a bit of it. And in my experience, I hate CNC. All them codes, oh my god. Like using the graph, the graph's way easier. But working with your hands is a lot funner, in my opinion.
I'd like to take off. Personally, I like CNC better. Way less time. All you gotta do, enter a code, send it off to the locksmith machine, and you're done.
And my experience in CNC was that all we do is just put the code in the computer, and then we tell what the machine does, and then what the machine does, and then whatever we put in the coding, the final product is. So my experience in CNC, my group will put in numerical codes in the computer where the machine will start sub-manufacturing, and the raw material in the machine, and the final product is done.
Alright, so my experience with CNC, so my experience with CNC, it's, as he said, it's just putting a bunch of numbers in a program and it cuts it for you. That came out. Personally, I think this is going to be like the future of manufacturing I think this is going to be the future of manufacturing. Of course, there's still going to be manual use for, as he said, more specific stuff, but like for like a more broader range, like more industrial pieces, CNC is like.
That's it for our presentation. Thank you. And I would like to give a special thanks to Mr. Warren and Professor Stanley. Thank you.
We can't take questions, sorry. We can't take questions.
Okay. If you have questions, just ask me later.
Everybody listen up. When I call your name, take your stuff and go outside the theater. So we're looking for Cadet Lillian Lazarde, Cadet Lucas East, do we have a Kendall Martin? Cadet Yvette Cruz.
I'm right here.
Cadet Victoria Harper. Do we have a Donovan Allen? Do we have a Cadet Donovan Allen? Do we have a Cadet Mull? M-U-L-L? Nope. And then I call Kendall Martin. Okay, that's it.
Lost. Hey, you're lost. You're going down.
We don't have time for questions. Good afternoon, Alpha Company. Good afternoon. All right. My name is Cadet Lawson. I go to Overhills High School. Now.
I'm Cadet Anna Baskins, and I go to Andrew Jackson. I am a rising sophomore.
My name is Nevaeh Brown. I go to North Romeo High School, and I'm a rising senior.
My name is Samantha Kennedy. I go to Ridgely High School, and I'm a rising senior.
My name is Cadet Chambers. I go to R.J. Meredith High School. I'm a rising junior.
My name is Tiger McCray. I am a rising junior at Thompson High School.
My name is Crystal Ventura. I go to Triton High School, and I'm a rising senior.
My name is Alexio. I go to Triton High School. I'm a rising senior.
My name is Victoria Harper. I'm a rising senior at Ridgely High School.
All right. So we had a presentation on additive manufacturing. Before I get started, I'm just going to go ahead and pass this around very, very quickly. This is a product of our 3D printing. You can look very closely at it and see all the layers. that. I just wanted to give a really special thank you to our professors, Professor Stanley and Mr. Warren. So give them a round of applause.
Alright, so what is additive manufacturing? So unlike subtractive, where you take that raw material and you're cutting pieces off, additive is you start from nothing and build it from the ground up. So there would be no scraps or things removed from the object.
Alright, so there's 6 main steps. Step 1, you need to figure out what you need to make. Step 2, you gotta create the drawing. Step 3, verify all the measurements, the unit. Step 4, you need to send it to the printer. Step 5, you need to actually start printing it, which can take a few hours. And step 6, you need to verify that your part is correct.
This is a time-lapse video of a 3D printer creating a 3D dragon.
So we're only going to watch a second of it because we're really short on time.
I'm watching a video.
Video? Looks like we're not watching a video. So, we're going to move on to how does additive manufacturing help? So right here is a picture of a design of one of the houses that people are currently building for homeless people. 3D printers are not only used to make small projects, they are made to use pieces into bigger projects. So right here you can see that they're making the outline and drawing all these things together. So at the end of this, they will have 3D printed houses for homeless people. So on this slide, we compared 3D printing and resin. Just double click on the screen. So 3D printing is better at producing larger and stronger parts. It contains less detail than resin printing. A professional 3D printer can cost from $4,000 to $20,000. A basic one, which is like, I guess for like hobbies and stuff like that, it could be around just $3,000. It's stronger than, like the stuff you get from 3D printing is stronger than any resin printed product. The filament costs less than resin, and the filament can't be reused. So sometimes you print things with the 3D printer, and with the filament, sometimes there's like extra pieces that are hanging off, and you can like melt those pieces and reuse them, so you don't waste any filament.
Resin printers form parts from liquid which carries and solidifies and is exposed to UV light. Resin printers have advanced quality with the advance to create small details on models with no visible layer and invisible lines. Resin printers can print numerous objects in the same amount of time as a single one. The total cost of resin printers up to $200 to $2,000. And I'd like to add something on the fact of that as well, a negative about resins, printers. The liquid that you use to create the resin printer, to create 3D models in the 3D printer, costs over $2,500. So you have to be very limited with your usage of the resin printer unless you want to keep paying over $2,500.
So, as you can see here, I have 2 of these little chess pieces. They're called ropes. This was the exact picture used to make these on the 3D printer. Some benefits to using a 3D printer are that you can ensure all items are made correctly before you print them. You can make multiple ones of these at the same exact time and in different colors. That's pretty much it. And over here we have some examples of different other prints, which include a dragon head, a fox, and SpongeBob's house.
All right. Anyone have any questions, comments, concerns?
I'm gonna see if I can get your video to play while you're answering questions.
All right.
Why is resin so, is resin a 3D printing more expensive? Resin, why is resin more expensive?
The equipment that you have to use in manufacturing, like I was talking about, the liquid, it costs a lot of money. And you only have the best way to make money online. You only have, if you really want to use all your product out, you should probably not, because you just have to keep in maybe thousands of dollars, maybe thousands of dollars. Unlike with 3D printing, you can just keep doing it over and over again, no losses.
And resin is mainly like only used, like say if you have some kind of art project or anything like that, any sculpture that like needs to like really focus on details. That's what mainly resin printing is for. Because it mainly just like
nobody's talking about is something you've never heard of before.
Specific details on whatever you're printing.
Right here you can see that a rainbow architect of a 3D dragon is created at $20. Unlike resin printers, 3D printers doesn't need liquid to create this object, only this limited time.
And depending on which type of machine you have, depends on whether or not you can make a big model or small model.
Any other questions?
Yes.
How do you make resin? You just throw it in the pot?
Actually,
well, not resin, 3D printing.
Oh, 3D printing?
Yeah.
You have to. What's the website called? Or you want to take over?
So there's a specific website you have to use, and you have to get it connected to your 3D printer. And on this website, you can take photos of different things that have been made already. Whether it has one or many parts, it can still all be printed. Does that answer it?
So just like name a random object that you probably want to create. Right?
My question was, how do you remelt down the material, the extra materials?
You don't melt them. You just put them into another roll. You recreate a different roll.
Excuse me. So would y'all say that like 3D or resin is more accurate or better and why?
Okay. Well, it's actually just better quality, and it doesn't have like defined lines, like for the layers, as the 3D printer makes. So, if that answers your question.
Yes. Oh. Yes.
Right there.
Okay. How long do products that you make from these last?
It depends on what you make it. If let's say you want, say how long does it last? How long do those chest pieces last?
It's like any other plastic product.
It depends on the exposure to UV ray, UV light. So that'll cause it to deteriorate a lot faster. But if you keep it in a environment just like a regular plastic, like they said, it can generally last for years.
All right. Some more questions.
One last question. No more questions?
No more questions.
No more?
Guys are done.
And so our last group to do their presentation is going to be electrical engineering. So I will invite their instructor and team up to get settled.
Hey, just 1 minute.
Our presentation for today will include basic concepts that are used in everyday life in electrical engineering. Start off with our basics, go into Ohm's law, the difference between energy power and electrical power and energy, and conclude with a summary of 2 experiments we did to prove these concepts. Starting off will be Cadet Reyes with electrical basics.
Can everybody hear me? Whoa! Can everybody hear me? Whoa! Alright, let's get this party started. So, the basics. I'm sorry my voice sounds like this. I swear I don't sound like a girl. So, in 600 BC, during the ancient Greek era, electricity was invented. There are 2 types of electricity. Static electricity and electricity due to the flow of charged particles. Now, electrons have a negative charge, as we all know. Free electrons move randomly because they aren't attached to an atom. The current is the flow of charged particles, and if the net current is 0, there will be no undirected free electrons. Okay, so voltage. Force and pressure is needed. It is needed when to push electrons into the same directions. The pressure is called voltage. Voltage source pushes electrons through the wire, which is called the conductor. Without voltage, no current can flow, which is like water. With no pumping system, it will not flow, and it will just stay there and stay there. A power supply establishes voltage, so a battery is a voltage source. Okay. Schematics. Schematics are a way to represent circuit using specific symbols. For example, a battery on the supplier of the circuit. The plus and the negative on a battery are symbols. You use that when you're putting in the batteries to make sure you put on the electrons and the protons and whatever else. So consumers of electrical powers are called loads. Resistance is the opposition of electrical currents. Okay. And here are the units and measurements. So we have the unit of current, which is an ampere, which is a symbol A, and it was found by Andre Marie Ampere. And we have unit of voltage, which is called volt, which is represented by V or E, and it was made by, well, not made, but found by Alessandro Volta. And the units of resistance, which is called ohms, which is that little tiny symbol right there. So it was founded by George Simon Ohm. And this concludes electronic basics. I hope you learned something about the current flows and the voltages. I will now be followed by Ohm's law, presented by Cadet Hunter.
Ohm's law. Ohm's law is the most influential law in all of electrical engineering. Basic summary I can give for it, an example, would be that the effect is equal to the cause divided by the opposition. In electrical circuits, effect is the current, or the amps. Cause is the voltage, and the opposition is the resistance. It should be represented by this little equation right here. I amps equals voltage over resistance. We can find the different units of measurement using 2 different meters. An ammeter and a voltmeter. An ammeter measures the amps in an electrical circuit, and a voltmeter measures the volts. Through these, we should be able to determine the current draw in the circuit system and determine the proper levels of what the capacity should be. I've given an example for an example problem using a simple electrical circuit, which the supply of the circuit is a 110 volt battery. The internal resistance is 50 ohms. So to determine the current draw from the supply, we would take, according to Ohm's law, which is right here, we would take the voltage divided by the resistance, and that would give us the current. So the voltage would be 110, resistance would be 50, 110 divided by 50 is 2.2. The solution, I would equal 2.2 amps. So how we did this, how we proved this with our experiment. Our experiment was that first we built a circuit, and then we started to create an Ohm's law. plot. The Ohm's law plot is used during the line. It's a linear plot that shows the change in voltage and how that would affect the different measurement of the amps coming out. So if we vary the voltage, we also vary the current drop from electrical circuit. It is represented here on our diagram, what we did. So as you can see, as you change the voltage in the circuit, you also change the current. In this diagram, the resistance is set for 2 kilo ohms. And we just basically messed with the voltage in order to do that. So according to Ohm's law, this table would represent, we would take voltage that we would put there and divide it by 2, which is the resistance 2 ohms. So for, say we put 2 volts into a circuit, divide that by 2, which would equal 1 amp. The note is in milliamps. That's the end of my presentation about Ohm's law. And next is electrical power and energy, presented by Deb Pratt.
So Kirchhoff's law basically states that all current flowing into and out of a node have to be equal no matter what. So most electrical nodes, as it says, are connected in parallel. And again, all nodes, everything flowing into it current-wise will always be equal. And the voltage is also always the same for each individual load. So electrical power, as you can see, each of these have a abbreviation for them. But to find power, you can have, there's 2 different equations to find that. You can either have voltage multiplied by the current, or you can have energy over time, and that's how you find power.
Can you speak up?
So for electrical energy, better, cool. Again, you each have your individual abbreviations, and energy again is power multiplied by time, and there's multiple equations for that. So to find out how much energy is used for a period of time, you do power multiplied by time, which you can again break that equation down as well. So everything has its individual thing, and then WT is the sum of all individual quantities put together. So whenever it comes to controlling your control over electricity, how much you pay, that rate is fixed by your utility company no matter what. Your voltage also always stays the same. Your current, however, varies on what appliance you're using, and then the duration of time that you use that is completely in your control. So if you have a microwave or an oven, you 100% determine how much time you use that, and that can be used to lower your bill from your electric. And then we'll be followed by electronic security systems, presented by Deb.
What's up, y'all? Alright, so I'm going to be running y'all through electronic security system. Y'all can hear me, right? Am I good? All the way back there, y'all can still hear me? Alright, so these are the parts of our electronic security system, being the Arduino board, the ultrasonic sensor that I'll get into deeper on later, our breadboard, our jumper wires, our resistors, our LED lights, and our buzzers. These are our Uno board features, which are displayed here. It's awesome. These are our ultrasonic features and pinpoints of it. I would like to highlight really big. The sensor has a transmitter and a receiver, and this is our transmitter and our receiver. And this is how our sensor works. So, our sensor measures the distance of an object using sound. So the sound would come out of the transmitter, reflect off the object, and the receiver of the sensor would receive the sound wave. I'll be followed by Cadet Jeff Paso.
So, can everybody hear me? Whoa! Alright. So, it was just explained my fellow cadet over there about how the sensor works. Now, to calculate distance, it is distance equals speed times time. No matter what you use, that is the calculation of distance. Now, the speed of sound is 343 meters a second. Very fast. So, the formula for distance from the object, from the sensor, is 0.0343 times time divided by 2. You have to divide by 2 because if you don't, it'll double the time. Because you need to have the time there and back. Now, this is the circuit that we use connected to the Arduino board. So, as you can see, these are all the pins and the connection of them. Now, like the green pin here, it is connected to the 10th pin in the Arduino board and connected to the green LED light. So this is the code and the connection of the pins and how they correspond to the code. The code's actions here would be to send out a signal to the receivers like the LED lights and the buzzers. The computer code will also calculate the distance for us so we do not have to do any extra work. So, here we have more code. The green LED light will turn on when whatever object it is 30 or more centimeters away from the sensor. The red LED will turn on when the object is 15 meters or less away from the sensor. The red LED light will also turn on with the buzzer. This is our final product. We have our wires, our LEDs, our resistors, buzzer, and the sensor. And that is the end of our presentation. Do we have any questions? Any questions? No? All right.
I know what y'all want.
It's so hot.
So, I'd like your attention here for just a little while longer. First of all, I want to give a big hand to all of the Alpha Company teams for doing good on your projects and your presentations. I hope that by seeing all these different presentations, it gave you a chance to see a little bit about what some of the other groups were doing. Each of you got one of these 6 modules. But now you've been exposed a little bit to what happened in some of the other modules. I can tell from your presentations, you guys learned a lot and worked really hard this week. So I give my hand to you guys in terms of the work you've done. I also want to thank both my module instructors and the cadets themselves for keeping on time such that we are actually done early. So you are not waiting to go get dinner.
All right, so how's everyone doing? Well, it's great watching you all with these presentations because this whole week has been building up to that moment. And so I've been in and out of here and also over in my office watching on Facebook Live. I've been really impressed with the way that you guys came together. You know, a week ago, many of you didn't even know each other, and look at you all today. You came together as a group and put together a project here. I mean, folks who were just listening to me, I thought you may not even high school students, but you challenged yourself, and that's very good. But I want to take just a minute to say that this camp has been in the works for quite a while. Has gone on a roller coaster ride of ups and downs until we got to this point. We are here because of the efforts of many individuals who didn't give up and who were innovative and out-of-the-box thinkers just like you, who brought people together and said that we can do this. Dr. Cash has been a very, very important part of that. She's assembled this team of instructors and professors to come here during the summer and give you this instructions. They've looked at what material will be most appropriate for you as high school students to get that collaborative experience and hands-on activities. And it's been very successful. So, on behalf of all of the cadets, I would like to present you with a small token of our appreciation for your on-time support to our campus.
I do appreciate it, and just like I had said when I was moderating the career panels for you guys, as a STEM teacher, which is one possible STEM profession you can go into, we need all the engineers working out in the industry, we need the scientists working in the lab, but we need good science teachers too. And as I said at that time, the thing that brings my heart joy is seeing students learn. And to sit over there, and yeah, I was watching the time and speeding some of you up, but to see how much you have learned this week and the concepts that you now understand and the questions you were able to ask the other teams, my heart is glowing here. My feet are tired, but my heart is glowing. So thank you guys very much. I'm going to turn it back over to ROTC for you guys to get organized.
I do like 8 of
That's not